So without further ado, I'm going to pull up our first speakers for today. And we're going to have Zicklag. Hi,
Hi there.
welcome. I'm going to put up your slides and leave the stage to you. And I'm super curious to hear how Bevy and Bones play together and how can someone accidentally make a game engine. So please take it away.
Okie dokie. Hey everybody. I'm Zicklag and I've been working on Rust game dev on and off for the last 5 years. And I started using Bevy when it was publicly announced 4 years ago. I'm self-taught and I've been learning everything from Rust graphics, programming, and just trying things out and doing whatever I needed to get stuff done. I'm super excited to be here, and today I'm going to talk about the journey me and the Jumpy community took as we accidentally made our own game engine. So a question you might be asking at this point is, isn't this a Bevy meetup? And of course it is. But as you'll see, our engine, Bones, has learned so much from Bevy that it would have been completely impossible to make Bones without it. And Bones is kind of like Bevy's little brother. And that brings us to what is Jumpy. Jumpy is a 2D multiplayer shooter game. It's all about great local play, fast reflexes, and importantly, modding. 2 years ago, when I took over as the lead developer for Jumpy, it was already using MacroQuad for its engine. I had more experience with Bevy though, and we were already using Bevy for another game, and we could share a lot of the knowledge and resources between them if we used Bevy for both. So we decided it would just be the best option for us to rewrite Jumpy to run on Bevy, and I was really excited. I started working right away and things went really well. We got the maps loading and physics ported, the main menu, and we even had to start to an in-game map editor. And it was all in pretty good time. And then came the real challenge and something I had never done before. That was networking. I started off by trying the simplest thing I could think of, a headless Bevy server that synchronizes transforms with the clients. While this kind of worked, the skipping was completely horrible. It was just unplayable. It also had a bunch of networking code that we had to add mixed in with the gameplay code, which was annoying and complicated. Like when you used an item, it now had to send a network message so that the item would get used properly across the different clients and such. It was just hard to maintain. And then the game was different on the network version than it was on the offline version. So I did a bunch of thinking and research and realized that to fix the skipping and get the gameplay smoother, you had to compensate for the network latency. And that meant syncing with the server and then fast forwarding the game in the background before you display the frame to make up for the network delay. That looked like it would be possible, but if I was going to go through all of that trouble, I thought it was worth looking at another option first. I had heard of peer to peer rollback networking, which was really cool because it didn't require a dedicated server. The clients could connect directly to each other instead. On top of this, the gameplay code could stay the same during network and offline play instead of having to mix network messages in with the normal gameplay. The caveat was that the gameplay had to be deterministic, and you had to be able to create and restore snapshots of it. Jumpy is a simple game, so that didn't sound like it'd be too hard. Lucky for us, Bevy also had a plugin for peer to peer rollback networking. So we started testing out the Bevy GGRS plugin, and we were really happy with how much it simplified the game's code. But we started to have some serious problems keeping the game deterministic. Bevy is designed for maximum performance and multi-threading, and that's often in conflict with determinism. Doing normal things like iterating over a query turned into a problem because now we had to collect the query results into a vector and then sort them to make sure that the iteration order was deterministic. Many things in Bevy are impossible to snapshot and restore. So the more things we did, the more gotchas we found. We couldn't use global transforms, we couldn't use local system params or events. These were all things that were like super easy to miss. And now with every change we made, we risked unintentionally breaking the determinism. This is really bad for new contributors and just for overall development peace of mind. So I did a lot of thinking about what it would take to put Jumpy's core gameplay logic into its own deterministic box, so to speak. We can make our own tiny ECS and make the whole world clonable so that it would be trivial just to snapshot and restore it. I started off with Plank, the simplest Rust ECS I could find. We forked it, we called it Bones ECS, and made just a couple tweaks to make it more suitable for scripting. But scripting would come later. Now we started migrating the jumpy gameplay code from the Bevy ECS to the Bones ECS. This was the biggest rewrite, and there was a lot more boilerplate than I imagined, but we did finally get the game working again, and we had a very interesting architecture. When the game starts up, it shows the menu and it's just a normal Bevy game. But when you start a match, it creates a new Bones ECS world and starts sending the controller inputs to it through GGRS. The jumpy gameplay code all runs inside the Bones ECS, and it creates entities for the sprites, cameras, tile map, etc. On each frame, a Bevy system will then read all of the sprites out of the Bones world and render them in Bevy. So as a player, it looks like nothing has changed. On the inside, though, GGRS is able to make snapshots of the Bones world whenever it needs to, and all the gameplay inside is completely deterministic. It was working, we had network games, and we were excited. Things weren't perfect, though. For one, now we had two ECSs to deal with. This was confusing, especially for new contributors, and there were other annoying things like having to put the GUI stuff in Bevy and the gameplay stuff in Bones. So we started to work on a unified Bones framework. The framework would allow Jumpy to use Bones ECS for everything, but in the background, we would still use Bevy for rendering. The first step to creating the Bones framework was to make a proper asset server. We had this planned since we had started working on Bones ECS and realized that integrating the Bevy asset server was not working very well. We had to do like handle translations and stuff. It was just kind of cumbersome. We'd also had some very specific goals around modability. For one, we wanted user asset packs to be first class citizen. We wanted uh, basically our own organized way to load asset packs in the game. And for two, we wanted a easy way to load all of our game config and assets easily through YAML files. So we had already had this set up with Bevy where we could use a derive macro to automatically generate asset loaders from Rust structs so that we could load the Rust structs from YAML files with Sirdi. Things got complicated though when we wanted one YAML file to be able to reference another YAML file or another asset. It kind of worked, but it was kind of a pain, and it was like half automated and half manual process. Having our own asset server would let us support both these use cases seamlessly with a first-class developer experience. And it would also help with scripting in the future. When it came to our YAML asset system, things were a bit harder than I expected, and that was because I was trying to support runtime defined asset types. The use case was for modding. So currently, each of our YAML assets were derived from a Rust struct, and the loader wouldn't load the YAML if it didn't have exactly the right fields for the Rust struct. I wanted to keep this type checking, but allow mods to define their own types that didn't exist in Rust. So we wanted something kind of like a JSON schema for our asset types. After some experimentation, I realized that this was exactly what we need for scripting too. This spawned the development of the Bones schema crate. Bones schema is very similar in purpose to Bevy Reflect, but it works quite differently. Where Bevy Reflect uses trait objects, Bones schema defines a stable memory layout. Basically, you derive the has schema trait and you add the repc annotation to your struct. And now you can get a schema describing the exact memory layout of the struct at runtime. It can also be created for types outside of Rust so that you have a schema describing a type that doesn't have an equivalent Rust type. Once we got this working, it actually simplified our ECS code quite a bit. It made the whole ECS compatible with runtime defined types. It was a huge step in the direction of scripting. After a lot more work to get everything tied together, we finally finished the Bones framework and finished migrating Jumpy to it. Now Jumpy was 100% a Bones game, and there was no longer confusion around having two entity component systems. On top of that, Jumpy and the Bones framework were now renderer agnostic. We are currently using Bevy as our rendering backend, but we could easily use anything else. In Bones, we only have four different kinds of renderables at its core. We have sprites, tile maps, debug lines, and EGUI. Any renderer that could display those four renderables could be used as a rendering backend. We could also integrate with Bevy plugins if we wanted to later for things like particles and 2D light effects. It wasn't totally restricted. We could add what we needed as we did. Now that we had Jumpy migrated, we were tantalizingly close to supporting scripting, and we had been waiting for this for a while. We had already been in contact with the author of the Piccolo Lua VM in anticipation of it, and all we had to do now was plug it in, or hypothetically anyway. It turned out to be a lot more work than we thought, and like every other step in the process, but it was worth it. We were finally able to demonstrate adding a brand new item to the game with a Lua and YAML asset pack. Personally, this was a huge deal. I had been working on getting modding into multiple game engines for nearly 8 years, starting with Godot, and every time I failed. But finally, this time, it was working. And that brings us to today. Bones continues to work really well for Jumpy, and we really like it. It does exactly what we need, and we're free to grow it however we need to, along with Jumpy and our other games that we'll be building on Bones. Something that we want to do in the near future is to try to make our own renderer for it. Bones' rendering needs are really minimal, and right now pulling in Bevy and its ECS and its reflection system and its renderer is just a lot more than we need for Bones. Also, properly integrating Bevy's renderer with Bevy's renderer basically means we have to write a custom sprite pipeline for the Bones world, which isn't really that much easier than writing our own renderer right on top of WGPU directly. We're hoping that this will cut down on dry compile times, which are they're not the most important thing in the world, but it has been an impact to new contributors. So it's something we were just hoping to trim down a little bit. So we never meant to make a game engine. We started just building these pieces bit by bit that we needed, and it ended up coming together even though we had never planned on it. And even though we didn't plan on it, we're really happy with the way it turned out, and we couldn't have done it without Bevy. Bevy allowed us to continue working on Jumpy, which was really our priority, while making Bones piece by piece. Bevy was so modular that we could combine it with our own ECS, with our own asset system, and with all of these different pieces as we went, however much we needed for our game. And we learned so much from Bevy. Like, so many different pieces of Bones are just simplified versions of what you get in Bevy. It Bevy's design, discussions, and everything, it just helped inform the way we made Bones in so many different ways. So, to everyone who helped make Bevy what it is today, thank you. We couldn't have made the game without you. So, now I want to take some time to do a short tour of the Bones schema system. The schema system is probably the most interesting and original pieces of Bones, and it's also the piece that could be most useful to other projects outside of Bones. So it'll be fun to take a closer look at how it works. First, we're going to look at the simplest thing you can do. Here, we've just got a simple position struct with an X and a Y field. We're just going to derive has schema, clone, and default on it. The has schema trait has just one function, and it returns the schema associated to the type. To see what that looks like, we're going to get our position schema and debug print it. As you can see, we get a lot of stuff here. We're going to look at just a couple things for the moment. We can see that the schema tells us the short name and the full name of our type, which is really handy for debugging and for figuring out which type to import by name in scripts. We can also see what kind of data our position is. In this case, we see that it's an opaque primitive type. Since it's opaque, all we know about the type is its size and its alignment. That's not very much info, but it's just enough that we can insert it, for example, into an ECS. If we want any kind of scripting superpowers, though, we need more info. That brings us to the repc annotation. Here we have the exact same sample, but with the added repc annotation to our struct. Now when we run it, instead of seeing an opaque primitive type, we see a struct type. The struct tells us the fields of the struct, the names of each field, and finally, by looking at the schema of the X field, we can see that it's a primitive F32 type. The schema now has enough info for scripts to come in and edit the memory of the struct without triggering undefined behavior. The schema tells us what can safely be done with the data. And now we're going to look at what kind of abilities this gives us in Rust. We'll start by adding another struct, in this case, the velocity struct. And we're going to create an instance of both a position and a velocity. Next, we stick them both in their own schema boxes. So a schema box is one of the most used types in Bone schema, and it's in fact very much like a box dynamy. By putting the position and the velocity in boxes, we erase the type, so to speak, so that even though they are different types on the insides, they're the same type on the outside. This lets us do things like stick both of them in the same vector, which is impossible normally because every item in a vector must be the same type. Now we can loop over each box, and we can try to cast it to a specific Rust type. In this case, we try to cast it to a position and print out the positions fields. Or if that fails, we can try to cast it to a velocity and print out the velocities fields. And this isn't really that different than what you can already do with a box dynamy. So let's get a little deeper. Because the schemas now describe our fields, we're able to access them by their names at runtime. Here we have the same example as last time, but we modify the loop. Instead of trying to cast it to a specific Rust type, now we can use the asRef function to get a schema ref, which is similar to a reference dynamy. Unlike dynamy, though, we're able to extract fields by name from the reference. We use the field function to get the try to get the X field, and we unwrap it, which would fail if it didn't have an X field. And then we try to cast it, and we unwrap that in case it's not an F32. And we end up with our reference to F32, which we can print and show that we are able to extract the X field from every item in the list, even though one is a position and the other one is a velocity. This kind of ability is essential for scripting and also very useful for things like ECS World Explorers and stuff like that. We can also use Bone Schema for serializing and deserializing. For example, if we have this small YAML snippet that we want to deserialize into a position. We haven't derived the SERD deserialize trait for position, but we do have all the info we already need in the schema. So to start, we create a normal YAML deserializer from our YAML snippet. And this is just normal SERD YAML thing. Then we create a schema deserializer for our position schema. And we use that to deserialize the YAML data into a schema box, unwrapping it in case it fails. Once we have that schema box, we can try to cast it into its position and debug print it to show that it deserialized properly. This functionality is extremely useful in the Bones asset server, and it's how we automatically load YAML assets into Rust structs. So far, all of our schemas have come from Rust structs, but schemas can also be loaded from files at runtime, and everything works the same. This is crucial for scripts that need to be able to store their own components in the Bones ECS, even though there isn't a Rust type for it. And it's also how mods are able to define their own asset types, even though they may not exist in Rust. Finally, there's one more nifty feature I want to show you in Bones schema, and that's associated type data. Each schema has a type data store. It's just a container that you can put anything you want into. There are all kinds of things you can use this for, but it's easiest to explain with an example. Let's consider a potential use case in our ECS. When you add components to an entity, it allocates enough storage for that component on demand. If you were to spawn a bunch of entities, then it would reallocate storage multiple times. But if you knew that you're going to, for example, have thousands of our position component, it would be more efficient to allocate the storage for, say, 10,000 positions up front. We could indicate this by adding storage mode type data to our position component. For example, here we've defined a simple storage mode enum that has an on-demand option and a pre-allocate option. When we come down to our position, all we have to do to add it as a type data is use the type data annotation. And in this case, we stick storage mode on demand into positions type data. And that's all there is to it. I'll show you how to read that from its schema later. First, one more thing that is pretty nifty that we can do with type data is we can make them derivable. So here we have the from type trait, which we must implement from storage mode to make it derivable. This is a bit of a contrived example, but in this case, we just get the size of the type in bytes and we allocate 1,000 times that size in for storage mode. So whenever we derive storage mode on a type, it will just pre-allocate 1,000 times the size of the type. Then to use it, now instead of having to set a specific storage mode for our velocity, we can just derive type data storage mode instead. And it will call our from type function to go and generate the storage mode for the velocity struct. Finally, uh, we can try to use our schemas. So in this, or our type datas. In this case, we'll just pretend like we're the ECS and we've got a list of schemas that we need to allocate storage for. We throw our position schema, our velocity schema in there, and also the schema for string, which we notice we haven't added a storage mode for yet. We can loop over the schemas and then simply do schema.typedata.get to try and get the storage mode out. And it's an optional storage mode because we may not have added storage mode to the schemas. And if we debug print it out, we can see that we have our on-demand storage mode from position, our pre-allocated storage from velocity, and none for the storage mode of the string. And there are a lot of possible uses for type data. In Bones, we use them to specify asset loaders and custom deserializers when the default one isn't sufficient. Eventually, you'll be able to use them to specify custom bindings to scripting languages. They're basically the traits of the Bones schema world, and like everything else in the crate, they focus on giving you more access at runtime to things that normally only work at compile time. And you'll notice a lot of this Bones schema is very similar to Bevy Reflect. It can do a lot of the same things, but in we went with the schema system because it allowed you to interpret the types of the data without having to make function calls back to the main app. So if once you knew the schema, if you had like a C program, for example, you could do direct writes and reads from a pointer to that type. So you could read and write the struct without having to go and make a separate function call every time you needed to do something, um, because you were going through the dyn reflect that you would have to do in Bevy Reflect. I'm not sure if that helps performance. We wanted it to be as friendly to scripting as possible, so that was kind of the idea, but that's all untested. And really, it's just our own different take on how to do the runtime reflection. And that wraps things up. I'm super accomplished with what we've accomplished so far, or super excited about what we've accomplished so far. I'm really grateful for all of the work everyone's done before us and everything we were able to learn from. And I can't wait to see what's going to happen next. Bones and everything in it are public on GitHub, so if you're interested, you can check it out. We'll have a Q&A session here if you have any questions, and if we don't answer your question, feel free to reach out to us on Discord or GitHub. We're always happy to chat. Thanks for having me on here, and thanks for listening, everyone.
Thank you so much, Zicklag. That's a super exciting project. I want to start with one quick question that I had myself. What you showed at the end was super exciting in terms of the whole dynamic system that you built there. Is that already used in the game that you showed, Jumpy?
Yeah,
Is
that it
the game
basically
logic actually built on it?
so the game logic, the whole ECS that actually underpins like the whole ECS. Like every time you store a Rust type, it's actually using its schema to make sure it allocates the right storage and stuff. And it's not necessarily providing a lot of advantages until you get into adding Lua scripts, and now Lua can add their own types and stuff like that. So we're not extensively using like Lua mods yet. We have like an
Okay.
item in the game, but that system is still being used in everything, and it's actually how we get all of our assets loaded and stuff like that.
Hmm.
So
Hmm.
it's used throughout, but we haven't used Lua specifically a ton yet.
Hmm. Are you also planning to support other scripting languages than Lua?
Uh, we're not 100% sure what we're going to build into it, but it's absolutely possible to support anything other than Lua.
Hmm.
I had done some work with JavaScript scripting for Bevy, with the Bevy mod.js scripting plugin. And so I got a little bit of familiarity with the Dino bindings to V8 JavaScript engine, and we could probably do that. The logic for the Lua one was because it's common in lots of game modding circles, but also
Yeah.
because the Lua VM that we had was 100% Piccolo is 100% safe rust from the user interface or as us. So we don't have to write unsafe to talk to the Lua VM, which was very cool.
Hmm. Yeah.
Kyron, who the author, has done a really great job on it, and it ran in web without modifications because when we used JavaScript, we
Hmm.
tried to use the browser's JavaScript engine, and we ran into serious performance problems every time we had to jump back and forth frequently
Oh,
for
yeah.
the JavaScript. So that web support was probably our biggest guiding factor there, but
Hmm.
it's not hard to since all the dynamic features are already there. It's not hard to like add new scripting languages. It's more tedious, uh,
Yeah.
but no, it's definitely something that we want to
Cool.
something we're open to for different languages and stuff like that.
Yeah. That's pretty cool. And so the highest ranked question that I see here is: are you still following Bevy's development? And what do you wish Bevy would learn from Bones?
Um, oh, that's an interesting question. Um, so in honestly, Bevy's obviously doing a lot of really awesome stuff. What we found out was Bevy is just a different it's just got a different niche, so to speak, or a different end use case. All of its performance focus wasn't what we needed for our small 2D game that we wanted with to do networking play on. So I'm not sure that Bevy has much to learn from Bones, as much unless it's just realizing that there are use cases that it doesn't cater to as well as we felt like we needed what we needed. So I think it's really just a different focus. So we're kind of we're definitely like we don't multi-thread. We've left that option
Mm,
open. So we by no means restrict you from multi-threading, and we have some ideas for that later. But we're focusing mostly on maintainability for small code base and just adding only what we need as we need it. Whereas
mm,
Bevy has, I mean, 3D is a huge topic in itself. It's got cool new 3D rendering stuff, every release and all of that stuff. So it's obviously way faster and it's massively parallel and all of that stuff. So Bevy's definitely better if you want to build something that is going to really take advantage of all those things. So we're probably more comparable to like Macro Quad or Comfy or one of those smaller or Good Game Easy or something like that. So
mm,
we're kind of like, but we're still ECS based. So we really just took we took Bevy and shrunk it really.
mm. I mean, that actually ties into the second question that I see here. Like, why did you end up using a different ECS crate instead of using the Bevy ECS that was already a separate crate, I think, when you started or pretty early on, right?
Yeah, no, that was already separate crate, and Bevy's again done very good at modularizing things. But the Bevy ECS was not like snapshotable. So
Ah, so that was it.
we
Yeah.
couldn't just like clone it and
Mm,
when you iterate over it for the sake of performance, the items come in a random order. So we were really kind of like, okay, just and initially we didn't plan on making like a whole engine thing. I was just like, okay, I still want to use an ECS, but if I can't use Bevy's ECS, I'll just make vectors or I'll just do like the simplest, dumbest thing.
yeah.
And that simplest, dumbest thing was pretty cumbersome and it grew as time went on. But so it was really mostly just around can we just do things in the same order every time? And even
Mm,
the system scheduler runs stuff in a if you don't enforce an order, it runs it in a random order. So all of those things, it was just kind of it wasn't helping us very much because 2D pixel game, like we don't need the performance, and
mm,
it was providing a barrier at that point. So we were kind of
gotcha.
just going for the easiest way out.
Mm, yeah. You mentioned also compile times, and the question is, how does it compare to full? Like, if you compare maybe a game that you built in Bevy with a game built with Bones, is that significantly different in terms of compile times?
Um, so right now, um, Jumpy or so Bevy by itself doesn't have much, or I mean, Hello World Bevy compiles way faster than Jumpy does because we've included like a multiplayer networking stack with hole punching. We have a Lua
Mm,
scripting engine in it. So it's not like that Bevy is much bigger. It was just that Bevy has more stuff. We've kind of got two engines now. So while we've already got Bones ECS, we've got a Bevy ECS2. While we've already got Bones Schema, we've got
mm,
Bevy Reflect too. So it's not that like Bevy compiles slower than Bones, or at least I'm not sure if it does. We haven't like done that kind of comparison, but
mm,
it's that we are already adding a lot of stuff to Bones because we want to build in networking. We're building in all of this stuff, so it's all easy to access. We build in Lua scripting. Obviously, you can opt out, but um, so then just having duplicates of some of this infrastructure for our already long compile times because we're pulling in all this extra stuff, it's just something that we could kind of trim out. And there was and then the other thing was usability because we had a way that we could extract our bone sprites into the Bevy render system. We could kind of like cheat and steal the Bevy sprite pipeline and just we would inject a system into the Bevy sprite pipeline that would go and read our sprites as well as Bevy's sprites.
mm,
But on a recent release that broke, and I think we have to write our own sprite pipeline now. So then we kind of have to get into rendering again. So then it was like, okay, if I'm already like having to kind of write a proper Bevy pipeline now, then
mm,
it's probably not that much more easier than just writing a WGPU rendering pipeline, which again, we don't need render graphs, we don't need anything.
mm,
I've thrown sprites on the screen before with raw OpenGL and stuff like that. So it's not that big a deal when all we have is these four renderables and we just spit it out on the screen. So
yeah.
we're being very, again, we're shrinking everything, and in that case it just seemed
Mm,
like let's not make our contributors pay for that. And I mean, even in our case at this point, we're like, maybe it'd just be easier to write a custom renderer for this piece at least.
mm. Yeah, I mean, it's not a fair comparison because it's sort of like both still in one package, at least up until now, right? So in terms of compile time, it's like build Bevy and then build the rest of Bones.
Build at least a chunk of Bevy, then build, yeah, a massive
Yeah,
hunk of bones. So
yeah.
yeah, it's really just a
Okay.
way for us to trim stuff out.
Yeah, yeah. And I mean, at the end, there will be probably a comparison possible once you have your own renderer. Like, how much does it really change now in terms of compile time that the whole entirety is gone
Yeah,
from Bevy, right?
yeah,
Okay, cool. Zicklag, I would move on to our next speaker and defer the remaining questions to our conversation at the end. It was a pleasure to see what you're working on, and yeah, I'm hoping that both systems can learn from each other, and I'm also excited to see
definitely.
what's going to come out based on Bones. Thank you so much.
No, thank you.